Okay. Yes. Good day, viewers. Today we'll be having a very important topic to quickly discuss, and that is is the physics class. We'll be discussing about waves. Okay, so what is a wave? A wave is a disturbance that travels through a medium and transfers energy from one point to another without a permanent displacement of the medium. So we have different types of waves. Imagine you throw a stone into a pool of water. You see the ripples that are seen on the water surface. We can say these are examples of wave. That's wave on water. So or water wave. So we have different types of waves. So it's a disturbance that transfers energy. It transfers energy from one point to another without the permanent displacement of the medium itself. So we have a classification of wave. We should know that for wave, we have two types of waves based on mode of propagation. Based on mode of propagation. Based on mode of propagation, we can say we have the standing wave and the progressive wave. So what is a standing wave? A standing wave is a type of wave that arises from the when two waves are moving in different directions. The two waves having the same amplitude, same wavelength and amplitude, and when they intersect, you see a wave like this. Let me draw it with this. So you have, this is the source. By the time it reaches this end point, this one also returns back. They are having the same amplitude, the same wave. This will generate what we call, you will see some things like antinode, the node, antinode, node, antinode. And you already know that the total distance traveled by a wave in one cycle is lambda. So that means that the distance of a node to node equals lambda over 2. Antinode to antinode equals lambda over 2. You can see, let me use another marker to explain that. This distance here, this a wavelength, and that's a whole cycle, 180, that's 360. So then the distance between adjacent node and antinode, or antinode to node, is lambda over 4. The distance between a node to a node to a node, that's lambda, or antinode to antinode to antinode. That is, the distance from here to this next one is called lambda. So that's for a progressive wave. Then the other one we have is the progressive. This is standing wave. A progressive wave, on the other hand, is a wave which is a disturbance that transfers energy from one point to another. When you have, let's see, something like this. So this, a progressive wave, it transfers energy from one point to another. And under this progressive wave, we can say we have two types based on under progressive wave. Let us quickly look at the two. We have the transverse wave transverse wave. These are waves. Transverse wave, you will see the wave moving this way. This is the direction of vibration. Direction of vibration. The wave is vibrating this way, and the propagation. This is vibration. Whenever you have the vibration of the wave perpendicular to the direction of propagation, then you say it's a transverse wave. A transverse wave is a type of wave in which the direction of vibration is perpendicular to the direction of propagation. An example of this, all the EM waves, all the electromagnetic waves, e.g., all electromagnetic waves are types of transverse wave. We also have the wave on string, water wave also. Then let's look at and note for all the EM waves, velocity equals to F lambda. So we have to know that they all travel with the same velocity, and that velocity is the velocity of light, 3 times 10 raised power 8 meters per second. So you have to note that in your book. So that's for all electromagnetic waves. And okay, let me mention some of the electromagnetic wave. The Vox G. I use this code so that these stand for the radio waves, the infrared, the visible light, the ultraviolet rays, the X-rays, and the gamma rays. The radio waves, infrared rays, visible light, ultraviolet rays, X-rays, and gamma rays. Although we know that the visible light has another spectrum which we call Röntgen. When we get to another stage in wave, we are going to do that. Okay, for now, let us spend it there. Then the other type of wave is the longitudinal wave. Longitudinal wave. In longitudinal wave, you have to note that the direction of vibration this is area of compression, area of rarefaction, compression, rarefaction. So the distance between compression and compression is a wavelength. So this is the direction of vibration, and also this is the direction of propagation. Where a longitudinal wave is a wave in which the direction of vibration of the wave is parallel to the direction of propagation. So this is an example of longitudinal wave. A good example is a sound wave. Sound wave is a longitudinal wave. Now also note in this transverse wave, we call some areas, this area, the distance between this is a crest, this is a crest, this is another crest, trough to trough. The distance between two successive crests or two successive troughs is called a lambda. Distance between two successive crests or two successive troughs. These are troughs. These are the troughs. And the maximum distance or maximum displacement is called the amplitude. So these are the amplitude, the maximum displacement of the particles from rest position or from the equilibrium position. We call it what? We call it the amplitude. Now also note that in a wave, we also look at the frequency. Frequency talks about how many waves are there in 1 second. How many waves are there in 1 second? And it's always recorded in hertz or per second. Then we talk about the period T, which is the reciprocal or an inverse of f talks about what is the wave, how many waves were you able to cover in 1 second? No, that's for frequency. That's you can use this for the period. We have the time over the number of oscillations. So we are looking at the time taken for a wave, for a cycle to be completed. The time taken for a cycle to be completed. And okay, so these are few things that you have to note under this. Then the distance between from here, the distance of a complete wave is also lambda. Lambda, the Greek letter, which we use for representing the wavelength of a wave. So in this class, at least, we have been able to talk about based on the mode of propagation. Then let's look at based on the medium of propagation, based on medium of propagation. Now, if you're looking at medium of propagation, we talk about there are two types of waves here. Mechanical waves. The mechanical waves are waves that require material medium for their propagation. So when you look at the mechanical wave, like sound wave, like a wave on a string, wave water wave, these are waves that require a material medium. There must be a medium, is that solid, a liquid, or a gas, which is needed. Like in sound will need air. So it requires a medium for its propagation. Now, but the other one is electromagnetic waves. And that is all the reverse G. Let me write this as reverse G. All these are the electromagnetic waves, the radio waves, the infrared rays, the visible light, the ultraviolet rays, and the X-rays, then the gamma rays. They are all examples of electromagnetic waves. And of course, I've told us that the V equals to F lambda, or owing to the fact, so we also write that as what? Lambda over period, where you know that F equals is the reciprocal of this. So there may be formulas, there may be questions that will come from this, like radio station with a certain frequency, determine the velocity if the distance is covered, so, and the rest. So you have to know that formula is very important for this particular area in physics. Okay, let's quickly go through the equation of motion, the equation of a progressive wave. Equation of a progressive wave equation. No, sorry, equation of a progressive wave. That's okay. So looking at the equation of a progressive wave, the equation of a progressive wave can be written. Let's look at this waveform. If it's starting from the origin, you can write it as what? Y equals to A sine theta. But in the case where you have it not starting from the origin, or there's a phase angle difference, then you have to bring into consideration A sine theta plus or minus phi, where your theta stands for the angular displacement, and your phi stands for the phase difference. Let's call this equation 1. For this equation 1, let's look at theta equals to omega t, and phi equals to kx. Your omega is the angular velocity. We already know this, angular velocity. and the k is the phase wave number. We call it wave number k. The x is the displacement, linear displacement, and your t is the time taken. So when we put these two equations into this, so let's call it equation star, put star into 1. Then we have y equals to a sine omega t plus or minus kx, equation 2. Also, when we look at, I want to confirm that you can all see it. When we look at omega, which is the angular velocity, is given by 2 pi f, and your k is given by 2 pi over lambda. Let's call this equation star star. So putting star star into equation 2. You know this, we already know this from the previous classes. This frequency, where your f is the frequency of the wave and your lambda is a wave length, the wavelength of this. And also we can easily write this. We can write this as okay, so putting into this, we can have y equals a sine 2 pi ft plus or minus 2 pi x over lambda. This is equation 3. And looking at this, I hope I've told you that the A is standing for the amplitude. Amplitude A. So let's bring 2 pi is common in these two equations. So we have a sine 2 pi into bracket ft plus or minus x over lambda. Now let's bring this pi outside. So we have a sine 2 pi over lambda. When I bring pi outside of this, then I will have lambda ft plus or minus x. Lambda will cut into that, so plus x. And recall, let's call this equation 4 equation 5. Recall that v equals to f lambda. So we can write y equals to a sine 2 pi over lambda. Lambda f, or f lambda, is the same thing as our velocity t plus or minus x. Equation 6. All these equations from equation 1 to equation 6 are all equations of a progressive wave. Let's take one example before we end this part. So, example, a wave equation is given by 500 sine 500 t plus or minus 200 x. Find amplitude, lambda, that's the wavelength, frequency, period, and the velocity of this wave. Find amplitude. Now, this equation, we are going to compare. To solve this equation, solution. Compare with any of the equations that look like this. Comparing with the equation that we can see that looks like this is equation 3. Equation 3 looks so much like what we have here. So we are going to compare it with equation 3. When you compare this equation, we'll be able to solve for all the things that we asked to solve. The lambda, the everything, the frequency, wavelength, and so on and so forth. So, comparing with equation 3, we have y equals to 500 sine 500t plus or minus 200x, and y equals to a sine 2 pi ft plus or minus 2 pi x over lambda. So automatically we can say A equals to 500 meters. That's very simple and direct. Then to get for F, if you want to get the value of F, let's compare this and this, because this is the part that has F. So we compare with 500. So we have a 500 t equals to 2 pi ft. T cancels out t. So F equals to 500 over 2 pi. And that will equal to 250 over pi x. Then our periods can be gotten by this equation. T equals to 1 over F. In that case, T, which is pi over 250 seconds. So our T equals to pi over 250 seconds. That's all done. Then for the lambda, we have 200x equals to 2 pi x over lambda. X cancels out x. So lambda equals to 2 pi over 200, which you can also write as pi over 100 meters. Please, you have to remember all the units. So then for the final, which is the velocity, F lambda is our formula. We can use F lambda, we can use lambda over t. You still arrive at the same question, at the same answer. So F is 250 over pi times pi over 100. Pi cancels out pi. V equals to 25. This cancels out this. This in this 2.5 meters per second. And this is how to use the equation of motion to solve problems. So it's very simple and very direct. So let's take one question. One of my students asked this question, and it's on when we talk about node, that's the point on a stationary wave that where there is no motion, or we can say where the particles of the wave are at rest. And the antinode is the position where you have the maximum motion on a stationary wave. Let me take one question on that. One more question, then let me see. I think, okay. This is jump question. This is a jump question. A progressive wave is represented by y equals to 10 sine 1000 pi t minus pi x over 34. Two layers of the wave separated by the distance. So the two layers separated by the distance, that distance is 1/5 x, have phase difference of, so we are looking for the phase difference. And we know from this wave, our phase difference equals to pi x over 34. And so pi times 153 over 34. And this is how we solve it when you look at this equation. So before I get to this place, let's not rush. Let's compare it with this so that those of you that don't know what I am using here, you can be able to 2 pi x over lambda. So this is this. So let's look at it. In this case, we can say that 2 pi x over lambda is the same thing as 2 pi x over 34, and which is our phase angle. So our phase angle or phase difference is this. So when you impute the values times 153 over 34, and this will give us, when you use the calculator, press. So we have phi as 4.5 pi in rads. That's radians. So rads. But the options given in this question are in degrees. So how do we convert this to degrees? So converting to degrees, we know that 2 pi in rads equals 360 degrees. So 4.5 pi in rads equals to x. So our phi in rad, let's call it equals to phi. So our phi in rad, we can, when you do this, you have what? 4.5 pi rads times 360 over 2 pi rads. So pi cancels pi, radians cancels radians. So yeah, 180, and 4.5 times 180 will give us, that should be 810. So this gives us 810 degrees. And under this 810 degrees, now we have to, because this 810 degrees is a multiple of different cycles. And in a cycle, what you only have is 360. A whole cycle is 360. So 360, this 810 is more than this. So I can say how many times. So let's continue to subtract 360 from it. We have, what do we have for that? We have a 450. When you subtract 360 from these two, we have 90 degrees. So the phase angle for this question is in 90 degrees. Also, this 90 degrees is the same thing as 4.5 pi rads. So the last question, which we use to round up this class, using this equation of motion, equation of wave motion. A plane wave is represented by the equation y equals to 0.1 sine 200 pi t minus 20 pi x over 17. Find the phase difference. So we are looking for the phase difference in rads, so in radians, not in degrees, between the points. So we have point S1 is 0.25 meters, S2 is 1.10 meters respectively from the origin. So if you draw a kind of waveform like this, you will see that this one is 1. This place, let's say this is 0.25, and this part, this is 1.10. So we are looking at the phase difference between these 2 points, and we know that phase difference is 2 pi x over lambda, and relating it to this, we have 20 pi x over 17. So from this, we have x our x value 20 pi, our x value is from 1.1 minus 0.25, 1.10 over 17. When you press your calculator, you will discover that this gives us 20 pi over 17 times 0. I think that should be 0.85. 0.85. When you multiply this and this, we have 17 pi over 17 pi. 17 goes in this, so the phase difference is 180. That's a pi in rads. A pi in rads is 180. That means that the distance covered there is the phase difference is pi in rads. So this is how we make use of the equation of motion to explain to solve different questions. So yeah, sometimes you see the 2 pi. Note, you can see a question like this: a sine 2 pi, then the numbers will be here. That means you have to compare this equation with what the one that looks so much like it. Thank you for watching. If you have any question, you can drop it in the comment section. Please subscribe, like, and share it to your friends. Thank you. Have a blessed day.